we finished speaking about the blow up of the plane in the point, and today we will use it to build the space of initial.
This is delivered by Naomi and company, no?
This is my
Yours.
notes. Okay, so yes, and so today we will using the blow up we will construct the space of initial dot. So let me recall where we are. We obtained the Painlevé equation. It has such Hamiltonian. It is such a dynamical system which is polynomial in P and Q, and it appears that during the evolution we can reach infinity. And how we saw it precisely? We change, for example, p to 1 over p, and obtain such relations. Maybe I'm sorry, size is too small. Okay. We obtain such such equations, and we see that we can start from the point p0 equal to 0 only when q0 is also equal to 0. Yes, but and in this case there are a lot of trajectories which come or go to this point. So the result of this consideration is that we should go to infinity, but in infinity there is a problem to construct the space of initial data, because there are infinitely many trajectories through one point. And finally, what we want to construct? We want to construct the space that contain all solutions. So so they could be continued infinitely in both directions. It is the first one. And the second, that through each point it passes only one and only one solution. Okay, so let's do it. I prefer now to use the projector, because for resolving the Painlevé equation we need 8 blowups. So it's better to do the calculations with Mathematica. Okay, so yes, of course, symplectic form broke, so new coordinates, of course, is not symplectic, but for us now it is not important. Yes. At the moment we don't care about this. Okay, so so let me comment this. and even remove. Then I will paste it. Okay, so after change of variables, what happened? Sorry. I'm very sorry. I commented too much. Okay. So here is equation after changing of variables. And no, this is the initial equation, and this is equation after changing of variables. Okay, maybe. Is it visible normally in this size?
Yes.
Okay, so we take the equation after change of coordinates. It is as follows. You see, out 1485. And so we make the blow up. So we change the coordinates. We take P0 equal P1, Q0 equal Q1 times P1. It's one map. It's only one map. But for us it will be enough because here we have for this equation we have inaccessible point P0 equal to 0 because it is in the denominator. Yes. So we cannot take P0 equal to 0 when Q0 is not 0. Yes. So and as we saw it in the two example, in one map, such an accessible point, inaccessible line, such an accessible set, it is only on one map of the blow up. So we take the map where it is not situated. So for us, it's enough to take only one map for our calculations. So from this map you even see that we cannot take P0 equal to 0 because Q0 then also will be equal to 0. Yes, from these formulas. Okay, so after the change of coordinates, we finally obtain this new pair of equations. And you see that we still have a problem,
Yes.
but other one. So we have P1, in the numerator, and Q1 minus A1, Q1 minus A1 in the numerator and P1 in the denominator. Okay, so we should blow up in the point P1 equal to 0 and Q1 equal to A1. So, and the change of variables will be as follows. So we take also only one map because P2 equal to 0 is accessible only when Q1 equal to A1. Okay, so and after this change of variables, we'll obtain this equation on Q2. So, and it is already polynomial. We successfully blow it up this problematic point. So what we had? We had line P Q equal to 0, P equal to infinity, and we blowed up this point. So there will appear a line that denotes the direction. Yes.
So that direction is A1.
Because
you say that
no.
These are Q0.
Yes. So direction where we blow up second time is A1. So the second blow up lies on this line. So, and you see that these two lines is inaccessible. Yes. Except this point. Yes. They are inaccessible. First one is inaccessible due to first we saw it at the first blow up, and the second is inaccessible according to second blow up. So I will draw it in a bold style. This inaccessible lines. Okay. So, but we have also another maps of P1 times P1. So we should check, can we reach the point where Q equal to infinity, or both Q and P equal to infinity. So let's do it. So let's invert Q. So this is a case where Q equal to infinity. So we solve the final equation, and obtain such two equations. So you see that we again have just the same blow-up, just symmetric to this one. Sorry, I should write that. So this depends from minus A1. This minus, yes. Or no, from A1. Yes. So it is plus A1. Okay. So we blow up it in the same manner. Just P and Q change the order, and obtain these two equations. We have just the same problem. When P1 equals to minus A2 instead of A1, and Q1, sorry, and Q1 equals to 0. So we make the second blow up, yes, and obtain also polynomial equations. So this is a direct analog. So we have that this line is inaccessible, and here we have point minus A2, here blow up, yes, and here I draw just the line P, sorry, this is Q equal to 0, this is P equal to 0, this is Q equal to infinity. Okay, so the last thing that we should check is just this point, Q equal to infinity and P equal to infinity. It appears that it is the most hard. Okay, so let's change the variables, and we obtain the following equations. So we see that here is also is Q0 over P0 and P0 over Q0. So here we have two inaccessible lines, two perpendicular directions, where Q0 equal to 0 and P0 not equal to 0, and conversely. Yes. So we can take for our consideration any of the blow up map. So one inaccessible line will be out of this map, but the other will be on this map. So we let's choose such map. What we will obtain? We will obtain this equation, and you see that here we have 2 over P1. So we have in this map that P1 is 0 is inaccessible as it should be, because P1 is P0 and P0 equal to 0 when Q0 is not 0, cannot be realized. Yes. So you see, if P0 is if P1 is 0, then it is then in the initial map P0 will be 0. Okay. So it's inaccessible point. Okay. And here we have still something to resolve. So it's absolutely okay that we obtain that this two line is inaccessible. We know it due to this blow up maps. Okay. So, and here we blow up in the point 1. Yes, because here we have that P. Where is it? Here. We have that P1 is 1 and Q1 is 0. So after this blow up, we obtain the equation Q2. and the situation becomes seems to become worse, even worse. Yes, but these two, this denominator, we shouldn't we shouldn't say that this denominator is, so it's not important for us because it cannot be 0. Yes, because it's just p1. It's just p1. So let me maybe let me let me write. So when we take the first blow up, the formula is as follows: p0 equal to p1 q1, q0 equal to q1. Yes. So so we have that q, and in our equations we have q0 over p0, which become 1 over p1, and p0 over q0, which become p1. Yes, this was in the very first equation. Yes, so we see that uh, mm, uh, sorry, one moment. Yes, of course. So so we see that p1 is equal to 0 is inaccessible. Yes, because we have this in the equation. So, and after the second change of variable, where p1 q1 goes to q2, q will be also always q for our sequence now, and p1 will be 1 plus p2 q2. So now this cannot be 0. Yes. So when we have such term in the denominator, it is already inaccessible. Yes, we throw it out from our manifold.
But so in that diagram, you exclude also the number line, or what is?
So we take, so here this line is p1. So this line is p1, and we take, for example, here we take the map for the first block, which doesn't contain this line, this inaccessible line. Here we also take the map which doesn't contain this inaccessible line. So we removed it just by taking one map. Okay. But here we have two inaccessible lines. So we take the map where we have where there is no this line, but there is this one. But it is still inaccessible. we just view it on our map. Is it clear? So our space of initial data will be not P1 times P1 blow it up in 8 point, but P1 times P1 blow it up in 8 point without some set of lines. So when we have such denominator, it's not important for us. But we have such problematic point. So we make this third blow up, yes, and obtain these equations. So it's even more awful. But these denominators, it is just images of. It is still the image of P1. So this awful terms is not a problem for us. We exclude the point. We already excluded the points where the denominator could be 0. But we have this one. So fourth time we make a blow up, and we obtain very awful formula. But it's okay for us because it contains only image of P1 after 3 blow-ups in the denominator. Yes. So it's maybe hard to see. So you should check that there is no other denominators here. Yes. Where it starts. Yes, so it starts here. Okay, so finally, what we obtained here, so this was first blow up, this is the second one, here in the point 1, here is the third blow up in the point T, so it's inaccessible. Here's the first blow up, and here in the point like here's I think minus t, and here it's like t1 plus 1 minus a1 minus a2, which is denoted by a0. And here we have the last one blow up. So the last one blow up will be, of course, accessible because the last exceptional line will be accessible because we have no problems in the final equation after 4 blow ups. So finally, we obtain the structure, the space of initial data of Painlevé 4. We make the following 8 blow ups. Of course, because we. So this is of course already inaccessible. Yes. Okay.
What are the eight blocks? Can you resume?
2 here, 1, 2, 2 here, 1, 2, and 4 here, 1, 2, 3, 4. So we take and we remove this these bold lines. They are sometimes called vertical leaves. Okay. Okay, so So let's continue. So now we switch. So now we switch to the algebraic geometry, and I will now use a blackboard. But maybe for your maybe for your convenience, it's good to have also the text. So so let me make some definitions. First one is divisor. Divisor not in common sense, but in algebraic geometry sense. So so we take what is divisor? It is free linear combination of algebraic manifolds, submanifolds of codimension 1. So we have some space, and on the space we take some some manifolds which is given by the algebraic equation, and we can take we can formally make an abelian group which contain all such manifolds. But but such group is of course very big. It's too big for us. So let us introduce odds. There are different divisors. This is called wave divisor. Divisor class group. So if we take rational function f, it has zeros and poles, like zeros of denominator. So f1 over f2. So so the set of zeros is f1 equal to 0. The set of poles is f2 equal to 0. So we can construct a divisor from the function f, which is just set f1 minus set f2. Was a rational function. So it is some divisor. And when we multiply rational functions, yes, So it's like f1 minus f2 plus j1 minus j2. So multiplication of rational function leads to sum of the divisors. So we have in the ring of rational functions, is it right to say ring, or maybe yes, maybe it's better to say field. Yeah, yes. I'm afraid, what about sum of rational functions? Maybe yes, maybe no problem. Okay, so yes, maybe maybe no problem. Okay, so we have inside the divisor group, we have the subgroup which is generated by the divisors of rational functions.
This representation, one over two works in some particular time map, but in principle, one has both zeros and poles. Just don't see this pose if we work in that time map. So
yeah, that's right, and even you can you can ask me about even simpler thing, because when we multiply such expressions, we can have some cancellations, but it is of course consistent with. Yes, of course, we can have we can have another maps, but nevertheless this relations hold.
yeah, but just class of F1 contains not only zeros of F1, it also contains zeros of F1 minus poles of F1, although they can be in some
Yes.
points which you don't use fine terms.
Yes. Yes. Okay. So and divisor class group is I don't know how to denote it correctly. So we take W and this is just divisor group, and factor it over the subgroup of divisors of rational function, and this group and the obtained group is rather small. Example. For example, for us it will be useful to think about P1 over P1. And we can take just line P equal to 0. Yes, we have such divisor. And we have also divisor P equal to any constant. For example, 1. Yes. So in the divisor class group, there are a lot of, there are infinitely many such such lines. But after the factorization, they are equivalent because there is rational function p over p minus 1. Yes. So so this function p has 0 in 0 and pole in infinity. P minus 1 has 0 in 1 and infinity also in infinity. And this function has 0 in 0 and infinity in 1. So when we take the difference of these two divisors, infinities cancel. They are not in our map, but of course it cancel, and we obtain this divisor. Is it clear?
I don't know why you want P1 times P1. You're using only P1, right?
Because yes, of course I use only P1, but it should be by the initial definition, it should be of complex codimension 1. But yes, but I want to speak. Yes, in this case, yes, but I want to speak about the line. Yes, so Pasha is right that he said that because we take only one coordinate from this P1 over P1, we can view it as lines for different Q, or without different Q as a point for one for one P1. Okay, so what's next? Okay, so we have so we want to define also rational map. So it's a map that from X there is non-empty open subset which is dense, open in the risky topology. So it's just given by is just obtained from some from so the closed for this topology is algebraic manifolds. So we take some such dense subset, and there is a map to normal map to. So informally it means that that in X we have some points or lines where we cannot define where we cannot define the map, but these sets are of codimension 1 or less. or more dimension. And birational map is when there is also inverse rational map. Inverse also rational. So when we have some we want so now my aim is to write what is the divisor class group for our manifolds, for our manifold which is P1 times P1, blow it up in 8 points. So we have that this space is a rational surface. This means that it is birationally equivalent to the projective plane. It's obviously because blow up is some local procedure, and we can to make this birational map, we can just remove this exceptional lines. Yes, is it clear? Okay. And for the rational surfaces, there is a theorem, the divisor class group, which denoted by pic X, Picard group. Picard group has also some other definitions. Maybe for algebraic geometry it's more natural, but we will use this one. So for rational surfaces, Picard group is the middle homologies of X. So initially, because what is the middle homologies of P1 times P1?
Two copies of Z.
Yes, 2 copies of Z. So Picard group of P1 times P1 will be Z plus Z. And when we make blow up, each blow up, because it's also a sphere, a Riemann sphere P1. It adds us also another generator Z. Yes. So for our case, it will be Z times 10, where 10 is 2 plus 8. And we denote the generators by H1, H2. This is P1. This is P1 cycles. Yes, so horizontal and vertical lines. And from the blow-ups, we have 8 exceptional divisors, which will be generators in our homologies. So this is the Picard group of our space. So as we will see later, all Painlevé equation spaces of initial data is P1 times P1 blow it up in 8 points. So the Picard group will be the same for all of them. Okay, because next, let us now introduce intersection form on this on the Picard group. So we can do it because it is middle homologous. So we can introduce a form on on middle cohomologies. Yes, which is just so if you take class of omega 1 times class of omega 2 and evaluate it on the whole manifold, on the fundamental class. Yes, so this will be form. It will be symmetric because these forms are these are two forms. Yes, because real dimension of our space is 4. Yes, so it's symmetric form on H2. And due to Poincare duality, this form induces also form on the homologies.
So is there anyone using this definition to compute something, or just intersection, geometric intersection?
I think that one moment, Pasha. I think that such definition is important to have a simple rigorous definition of the intersection form, because in some cases this intersections is rather non-trivial from the geometric point of view. So in terms of homologies, these intersections frequently can be understood very simply. This is just a number of intersection points of the two homology representatives. So this will be points because classes are of middle dimension. So when we intersect it, the intersection will be of dimension 0. So for example, if we take line H1, which represents by P equal to 0, and H2, which could be represented by Q equal to 0, then their intersection will be one. So yes, so they just intersect in the point 0, 0. If you take any other representative, you will obtain, of course, the same one. And H1 times H1 is 0. So if we take two the same representatives, it's not obvious because they intersect on their whole. But we should calculate transversal interceptions. So we can just take two different representatives, which of course don't intersect. Okay, and of course H2 is also 0. Okay, now let's go to self-intersections of E. And here we will to calculate its self-intersections, we will use some tricks. So if we have the blow-up, one blow-up, one H2, H1, yes. So initially we have just two lines, H1 and H2, which intersect in one point. After the blow-up, this H2 contains this line without this point, and this point becomes E. Yes. So and the remaining becomes H2 minus E. Yes. So this line becomes E and H2 minus E, and also this is valid for H1. So we obtain that H1 minus E times E equal to 1. Yes, because here we have one intersection. And so it's bilinear. We can write it in this manner. And to calculate self-intersection of E, we should know this self-intersection. But we know it. It's 0. Why? Because only these two representatives become H1 minus E, H2 minus E. Other representatives remain to be H1. So H1, here's the line H2, which intersect in another point. And because E is situated only in the point, I don't know, maybe let me write like 0, infinity. So H1 don't intersect with E, so this is 0. Finally, we obtain that self-intersection of E square is -1. And it is more hard to understand geometrically because here when we calculate it, we just move. When we have problem, we just move one of the representative, yes, and obtain 0. But the exception line is exceptional. It is the only representative of its class. So we cannot move it in ordinary way. Okay, so finally we obtain that E square equal to -1, and it is orthogonal to H1 and H2, and also we can ask about EI times EJ. So because when we make the blow up, only the representatives which cross these points became h1 minus e, h2 minus e, and another lines are still h1 or h2, and they don't intersect the e, obviously. Yes, because e is situated locally in the point 0, infinity.
So you're saying that h1 do not pass by 0.
Yes, we can take just another representative before the blow up, h1, and after the blow up it remains h1. Of course, in this trick I use several propositions and theorems like that intersection form remains the same after the blow up. So I will not speak about rigorous formulations, but this theorem holds. Okay, so finally, to obtain the intersection form on all Picard group, we should calculate EI times EJ. So using this trick, this is not very obvious that it is always 0. It's obvious when we take blobs just in different points. Then it's obviously 0. But when we do several blobs, it is not. Sorry, I should check what line is h1 and what line is h2. Okay, so this line will be h2 minus e1 minus e2. So e2, or no, e5, yes, of course it's called e5. Yes. So let's see. So we will speak more about this intersection form after we see the problem on our blow-up. So maybe it's better to draw it step by step, and that will be the final step of my today's talk. So initially we have just P1 over P1. So here is H2, H2, H1, H1. Yes. Then we make the blow-up. We denote it E1, and here is H2 minus E1, and here H1 minus E1. Then we make blow up on this E1. Because we're making the point which do not pass through these lines. So these lines remains the same, but E1 became minus E2, and this we denote by E2. Yes. So here we have that E2 times E1 minus E2 equal to 1. So we have that E1 times E2 equal to 0. Because self-intersection, we know that it is minus 1.
We already know that intersection of this exponential divisor